Two gas expansions go from the same initial state to the same final state at constant temperature. Path 1 is slow and reversible. Path 2 is a rapid free expansion. Which path does more work by the gas? A. Free expansion. B. Reversible. C. Same work. Or D. Not enough information. We'll reveal the answer shortly. In this video, you will learn the thermodynamic difference between reversible and irreversible processes, and you will practice calculating work for a reversible isothermal expansion of an ideal gas. First, the definitions. A reversible process moves in tiny steps, keeping the system essentially at equilibrium. At every moment, the internal pressure nearly equals the external pressure. If you reverse that tiny push, the system retraces the same path. On the other hand, an irreversible process uses finite driving forces, like a large pressure drop, so it charges forward and cannot retrace its path through the same intermediate states. On a pressure-volume diagram, the work done by the gas is the shaded area under the path. The reversible isotherm hugs a higher pressure at every intermediate volume, so its area and the magnitude of the work is larger than for any comparable irreversible path with the same endpoints. So returning to our quiz, the slow, reversible expansion does more work by the gas. That's choice B. Now let's build the actual work equation. Consider an ideal gas that expands reversibly at constant temperature. The work equals the negative integral of external pressure with respect to volume. For a reversible ideal gas, pressure equals N RT over V. Integrating gives us W equals negative nRT times the natural log of V final over V initial. The negative sign means work done by the gas on the surroundings. Next, apply this to numbers. Example 1. 1 mole at 300 Kelvin expands from 1 liter to 2 liters, reversibly and isothermally. Plug in the numbers. W equals negative 1 times R times T times natural log of 2. That is about negative 1,729 joules. The negative sign tells you the gas did work on the surroundings. Before we go further, here is a quick correction about other kinds of expansion. If the gas expands freely against a vacuum, external pressure is 0, so the work is 0. If it expands irreversibly against a fixed external pressure, use W equals negative external pressure times the change in volume. Do not use the reversible formula for an irreversible path. Here's a mini checkpoint. You now have the big picture. Reversible means quasi-static. Work is the area under the path, and you have the isothermal reversible work equation ready to use. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Now try a second case using the same formula. Half a mole at 350 Kelvin expands from 2 liters to 6 liters, reversibly and isothermally. Compute W equals negative nRT times natural log of 3. That gives about negative 1,600 joules of work by the gas. To stay accurate, keep 3 guardrails in mind. First, the volume ratio inside the natural log is unitless. But if you use pressure times change in volume, convert to pascals and cubic meters for joules. Second, our sign convention makes work negative when the system does work. Third, perfectly reversible paths are idealizations that set the maximum possible expansion work. To wrap up, here is a quick recipe for any problem. 1. Confirm isothermal and reversible for an ideal gas. 2. Write W equals negative nRT times the natural log of V final over V initial. 3. Plug in N, R, T, and the volume ratio. 4. Compute and interpret the sign. Negative means the gas delivered energy as work. In summary, reversible means inching along near equilibrium and tracing a path you could retrace. On a pressure-volume diagram, work is the shaded area under the curve. For a reversible isothermal expansion of an ideal gas, W equals negative nRT times natural log of V final over V initial. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.